So in this problem, we have two identical speakers broadcasting a signal with a certain frequency, and they're facing each other. There's a certain separation between them, but that's not specified in the problem. All right, so each send out a signal, and clearly from the superposition principle, the oscillation in between them, you have to consider both signals. You have to sum up the displacement caused by both signals. All right, the first part A of the problem is the midpoint between the two speakers, the location of a minimum or a maximum of sound intensity. Now, you got to be very careful about this problem because there's an obvious answer, and obvious answers are not always correct. In the midpoint, the point which is right here, halfway between the two speakers, consider the sound wave sent out by the first speaker. Okay, it traveled a certain distance, right? And then arrived at that point. Now, the second speaker at the same time sent out identical sound wave, right? Traveling to the exact same location after going through the exact same distance. So it is clear that the two signals arriving at the midpoint will have the same phase. Right? That means if one is maximum, the other is also a maximum. One is zero, the other is also a zero. And that might lead you to think that the midpoint is a interference maximum because after all, these two signals are in phase. Now, that wouldn't be a problem if the sound wave were a transverse wave, okay? So the first wave arriving at this midpoint at one moment, for example, pushes the air particles upward. At the same time, the second wave does exactly the same thing. It also pushes upward. So these two waves would enhance each other. The problem here is that sound waves are not transverse waves. They are longitudinal waves. So let's say at one moment, the first wave sends out a signal reaching the midpoint, and it happens to be pushing the air molecules away from the speaker this way. Okay, the oscillation has to happen along the line connecting along the line of propagation, which is this blue line, right? What do you think the second wave is doing at the very same moment? Well, because it's got the same exact phase. So if we're doing the exact same thing, that is, it's pushing out, it's sending out a signal which pushes the air molecules away from it at that same moment. But you see, these two waves are now pointing in opposite directions, right? They're pointing in opposite directions, which means the midpoint is actually an interference minimum. Okay, that is again due to the fact that the sound wave is a longitudinal wave. So when you add these two waves together, you have to consider that. All right, so that's a little bit tricky, but it really highlights the difference between interference between transverse and longitudinal waves. Right, so that was part A. And part B of this problem. What is the distance between a pair of adjacent maximum and minimum of sound levels? Well, the first wave does some, it's kind of like this. And the second wave is traveling this way. The second wave is identical in shape, but it travels in the opposite direction. And when you add them together, you're going to get something like this, right? It's a standing wave pattern. And each one of these between here and there, between two adjacent zeros, we have what's called a loop, right? And in the loop, you start with nodes of zero amplitude to antinodes with maximum amplitude, and then back to a node. So if you're looking for the distance between an adjacent pair of maximum and minimum in sound level, then you're looking at basically the distance between here and here, right? This is an antinode and this is node. And that is, as you can see, half a loop. Each loop is half a wavelength, and therefore the distance we're talking about is a quarter of a wavelength. Okay, so that distance is lambda over 4. And in our case, what is that value equal to? So lambda over 4. You're not given lambda, but you are given the frequency and the speed of sound. So lambda is equal to V over F divided by 4. And V is 340 meters per second divided by the frequency. The frequency is 160 hertz. And then you divide it by 4. And let's see what you come up with. 340 divided by 4 divided by 160. You got 0.53 meters. Okay, that is the distance between the adjacent pair of maximum and minimum, actually between node and antinode. All right, now, what is the ratio of I maximum over I minimum? Now, be very careful here because we're looking at intensity, ratio of the intensity, not the ratio of the amplitude. We know that the intensity goes like amplitude squared, right? And the amplitude at a node, a minimum. Right? At node, it's got minimum amplitude, right? The reason why it's got minimum amplitude is because this is where the two waves are pushing the particles, M molecule, in opposite direction. So if one of the amplitudes, the amplitude from the first wave is A1, and that from the second wave is A2, then you're looking at A1 minus A2. Okay. So in our case, let's see here. They didn't tell you A1 and A2 directly, but what they're telling you is that, first of all, these are two plane waves, so you don't have to worry about the amplitude ever decaying as you move further and further away from the source. Okay. But they do tell you that one loudspeaker delivers twice as much acoustic power as the other. Now, acoustic power P divided by the cross-sectional area, that gives the intensity. Okay, so they're not telling you A1 and A2, but they're telling you that I1 over I2 is equal to 2. So let's say the first speaker is a stronger one, produces twice the intensity as the second one. Okay, what about A1 and A2? Well, A is not equal to I. A is proportional to the square root of I, or we also say that I is proportional to A squared. Okay, so that's so that means that when I calculate A minimum, A1 and A2 are not equal, and they don't have a ratio of 2, but I do know that that A1 squared over A2 squared equals 2, or we say A1 equals the square root of 2 times A2. That's something we can use here. So it's square root of 2 A2 and then minus A2. Okay. That's A minimum. That's what happens at the node. Now, at the antinode, the reason why it's an antinode with the strongest amplitude is because at that point, the two waves are in phase. They push the air molecules in the same direction. So A maximum equals to A1 plus A2. Okay. And we already know that A1 is square root of 2 times A2. That's square root of 2 A2 plus A2. So now I can find I maximum over I minimum, which is what they're looking for. Right? I maximum goes like A maximum squared, and I minimum goes like A minimum squared. Right? So now I can plug in the values of A maximum and A minimum, the expressions. So the A maximum I have square root of 2 A2 plus A2, and then for A minimum I have the square root of 2 A2 minus A2, but don't forget the whole thing has to be squared, and that is the same as square root of 2 plus 1 over the square root of 2 minus 1, and you just have to square that. Okay, and then you get whatever value. That is the intensity ratio. Now we know the intensity is related also to the sound level. Right? So if we express find connection between the sound level and intensity, then we can find the difference in the sound level as well. So that will be the last part. Beta, the sound level, is defined as 10 log I over I naught. So therefore, for beta maximum, I simply use I maximum, so 10 log I maximum over I naught. And similarly for beta minimum, I have 10 log I minimum over I naught. And then just plug these two expressions in to get delta beta, which is defined as beta maximum minus beta minimum. This is the maximum amount of variation in sound level. As you travel, as you walk from one speaker to the other, you're going to encounter the variation of sound level. And this delta beta is the greatest amount of change in the sound level as you walk from one speaker to the other. And you take that. And we know that log of, this very common known identity, log of x minus log of y is equal to log of x over y, right? So you have here 10 log of I max over I min, right? And we already know from part 3, for part C, what is I maximum over I minimum. So we know this is log square root of 2 plus 1 over the square root of 2 minus 1, and then you square it, okay? And you can easily simplify that to get a numerical value. So this is how we solve this problem.